and good evening to one and all. I am Himanshu Thakur from Team IEEE BVMSP, and I welcome you back to the fifth session of the International Tech Conclave ITC 2020. And again, before going ahead, participants kindly keep a note. Certificates will be provided to only those who attend all the sessions of ITC. I request the participants to like the video and also subscribe to our channel. At the same time, if you have any, you can use the chat section, and our moderators will follow. Today, for the upcoming session, we have with us Dr. Archana Sharma, who would be talking about futuristic radiation-based space technologies. Now, I would like to call Dr. Bhargav Garodia, sir, Vice President in BVM Central Committee at BVM Engineering College. Further.
Hello everyone, I am Dr. Bhargav Garodia, Professor and Head in the Electronics and Communication Engineering Department at BVM Engineering College. On behalf of BVM Engineering College and IEEE Student Branch, I welcome all the participants to the fourth day and fifth session of International Tech Conclave 2020. It gives me immense pleasure to introduce today's session expert, Dr. Archana Sharma. Dr. Archana is a principal scientist at CERN laboratory in Geneva, Switzerland, and active in the field since 1989. She is an internationally recognized expert, worked on several CERN experiments, both on R&D involvement and in designing and prototyping, running laboratories for construction, safety, installation, commissioning, and operation of large-scale gaseous detectors for radiation. She is an examiner for European Commission Horizon 2020 project and for relevant national funding agency, and an adjunct professor in several institutions. She teaches regularly courses on gaseous detectors and their application in high energy physics and other fields like medical imaging and diagnostics, astronomy, space, and etc. And now, without wasting much time, I would like to hand over the proceeding to Dr. Archana Sharma and get started with the session. I request everyone to keep their microphone off to avoid the disturbances and when session is going on. Thank you.
And to all the student community, to colleagues for finding the time to arrange this seminar in these challenging circumstances. And I'm extremely happy to share with you the little I have learned over my journey here at CERN over the last 30 years. And I hope you can see my screen here. So I would share with you a bit of what we do at CERN, and then am I mute or am I? Can people hear me?
Yes, ma'am. Yes, ma'am, we can hear you.
Okay, thank you. So the question starts for everyone, ever since we were children, why at all are we here? And in search of answers, we have been scratching our heads, just like this thinking man here. Where did we come from? What is the world made of? And what holds the world together? Certainly you've heard about the Big Bang which actually started our universe, or the multiverses, which we do not know yet about. We know of the inflation, which transformed this very huge, hot, dense matter, or we don't even know whether it was matter at that point of time, this huge ball of energy, into particles or very tiny phase of matter, which we do not know anything about as well. So what we want to really go forward is to understand the origins of the universe, where all the particles came from where we have become stable, and how elements formed from the first nuclei that were formed in the first few minutes. The universe has been expanding. As you see here, the temperature is billion times from in the center of the sun when the whole thing started at the point of this Big Bang, which is called a singularity as such. And ever since, it's been cooling, if you look on the bottom scale, to the point where we exist now. And it's the process in between that is very interesting, to be able to understand why at all are we here. And in these very few fractions of nanoseconds, picoseconds, or attoseconds, and so on, we have no idea of how this kind of plasma or this kind of primordial material that was there, how that transformed into particles, and subsequently the cooling helped into the formation of the galaxies and the universe as we know it today. So, how can we try to understand about matter? We all know about the periodic table. Mendeleev has done this wonderful work, and all of us understand now how elements are arranged nicely in groups and periods, and we understand their properties as well. So, in the same manner, there has been a lot of study about matter, which you are all very familiar with. You are all budding engineers or senior colleagues. You all know about the studies that have gone on in terms of the Rutherford experiment, in terms of the balloon experiments from cosmic rays, and so on. And we know about the atom, about the nucleus, about the proton and neutron that resides inside the nucleus, that makes the nucleus, and of course the electron, the humble electron as well, which together make up the smallest building blocks of matter as we know them today. In addition, there are quarks, which are the composite for protons and neutrons. 3 quarks together make a proton, and another 3 quarks together make the neutron. So there are still questions whether there are still smaller particles, or are there unknown units? Are there pentaquarks, or are there tetraquarks, and so on? So these questions continue to plague us, and a lot of answers have been sought over the last century, gained knowledge that we have in the field of particle physics, cosmology, and so on. So in India, of course, these studies have been started very, very long ago. And if one goes and delves into the history of this field, we will find in India, we have a large number of scientists who have, in one way or another, contributed towards the understanding of matter, the understanding of the origin of the universe, the understanding of how particles behave, and so on. Now, what are the primary physics questions that are still open? The open questions are, what is the origin of mass? So when there was this primordial plasma, at that moment of time, there were all these free particles going around, and there was no mass as such. So how did mass come about? In addition, you have all heard about the mysterious dark matter, and it's called dark matter simply because we do not understand why there is 95% of the universe that we do not see. We can only account, with all the experimentation that we've done, with all the knowledge from the cosmologists' experiments, from all the material and data gained from the telescopes and from the Hubble telescope and so on, we only account for 5% of matter. So where is the rest? And the name given is dark matter or dark energy. In addition, you would think, and I think we all learned at high school, that there is something called conservation of mass, conservation of energy. Similarly, there must be something called conservation of matter, where if matter is produced, an identical amount of antimatter must have been produced. And in that case, matter and antimatter would annihilate, and we would just see a flash of light. But why is matter there? So what happened to the antimatter? Where is this missing antimatter? And what are the properties of this primordial plasma? So the answer lies in investigating this manual of instruction, how the universe came about. And for that, we need to go back in time. How do we go back in time? By recreating the Big Bang. Can we recreate the Big Bang? Now that is the question. Because until this point, we have understood clearly that matter is made up of atoms and molecules, and the atoms are made up of nucleus, where there are protons and neutrons, and there are quarks, and these are the subatomic particles. However, how do we go back in time? We have to first try to understand, just like the periodic table, we have understood now the standard model of particle physics. So without going into too much detail, I just would like to highlight to you about the quarks, that there are three families of quarks, and that there are two families of leptons, and three families of leptons, sorry, and each one of them comes along with a neutrino that is always formed whenever one of these are formed in nature. Now, we all know about the four forces of nature: the strong force, the nuclear force that the protons together, the electromagnetic force, the weak nuclear force, and gravity as well. So each of these forces is actually, it can happen because of the presence of gauge bosons, the so-called gauge bosons. We are all familiar with the photon, so let's speak about the photon, and which is the carrier of the electromagnetic force. And then, of course, we have the gluons, which is the carrier of the strong strong nuclear force, and the W and the Z bosons, they are the carrier of the weak nuclear force, which gives us radioactivity. So now it seems that we know a bit about the fundamental particles of matter, and we also know a bit about the four forces of nature. Together, they make the sun shine. Gravity holds the planets and the stars together. They give us our day and night, and it seems that we know a bit more about how what happened, or at least what are these subnuclear particles, very, very tiny, or the tiniest particles that actually exist. So in trying to go back in time, we would like to recreate the Big Bang. Now that's quite audacious, I would say. So how do we go about it? We do know about one equation that everyone is familiar with, that is E is equal to mc squared, right? And we also know that if we smash together at very high energies particles, then this energy available can actually convert into mass using this equation E is equal to mc squared. And that's the business that we do at CERN, where beams of protons can collide and generate in a very tiny space temperatures over 1 billion times higher than those prevailing at the center of the sun. So now this is the tiny big bang, which can be produced at accelerators, many parts of the world, but the largest accelerator on the planet is at CERN. What exactly are we doing here? Of course, the energy that we are talking about is huge, but it's concentrated as if it were on the tip of a needle. So just to illustrate the experiment, think about two of these mosquitoes that are billions and billions of them, but the energy is all concentrated on the top of a needle, and then they keep smashing into each other 40 million times in 1 second. And lo and behold, in these collisions, what we see are very highly expected particles that are coming out. By highly expected, I mean the particles that I showed you on that table, on the standard model table. And you see that those are the kind of things that we already know, like the cats and the dogs and the pigs and the elephants. And there are some hypothetical particles. So we do not still know how the mass came about. And in 1964, there was Professor Higgs and his team who had predicted that just like the photon and the boson, the gluon, and the graviton, for example, similarly, we have something called the Higgs boson, by which mass can be acquired. And if we are lucky, in these collisions, we might find particles that have now become extinct, but were present at the time of the Big Bang. So when you see here these kind of dinosaurs, for the dinosaurs, we know for sure that they did exist because we have seen the fossils. So similarly, we might find the dinosaur particles. But we might also find some unexpected particles like the aliens over here. And that's where we are looking towards what we call entering in the mysteries of dark matter, or candidates of dark matter. So here is a picture that shows you Geneva, CERN, where I am right now, a little close to CERN because now we are teleworking, so we are at home. You see the airport over here, and you see two little balls going around a circle, which represents the tunnel underground, 100 meters underground, and then it's colliding at some point. The circumference of this tunnel is 27 kilometers, and at various points around this circle, there are collisions that are happening, and these collisions then are studied by means of microscopes. So these microscopes are actually very, very big, very huge, and I will come to that in a moment. But just to point out that this is the scale of our understanding, so to speak, where when we want to study about galaxies and the universe, we look out there with the space station or with the Hubble telescope. We do cosmological studies with other radio telescopes. And when we want to go into the other direction, which means going beyond the smaller particles than the proton, than the quarks, we want to go to the Large Hadron Collider. And that's the super microscope called the Large Hadron Collider, or the LHC. And inside the LHC, there are collisions which happen, which we are executing for many months in 1 year, and it has been operational since 2010. And we have been converting energy into mass and then studying what's happening at these collisions by use of a large amount of technologies, of which I will show you some of the samples. So while we are reproducing, I just want to highlight one point to you, we coming from India, of course, and also being a proud Indian. I would like to highlight that at CERN, there is this sculpture which was presented by our Department of Atomic Energy to CERN as an acknowledgement of the work done by Indian scientists at CERN. तो सिर्फ हिंदी में इतना ही बोलूंगी कि ये नृत्य जो है, तांडव नृत्य है, इट इज कॉस्मिक एनर्जी एज वेल, और हर प्रोटॉन कभी कभी सृजन और विनाश के नृत्य की इस प्रक्रिया से गुजरता है. तो सृजन और विनाश, कभी कभी हम बोलते हैं India has a lot of scientific evidence towards the origin of the universe. So the documentation and the relationship between this dance is what we are looking inside our own little machine over here, not so little really. So with this machine, we recreate the Big Bang, and we go to very close after the Big Bang, which means temperatures are very, very high, as we said before. So we are nearly at 10 to the minus 10 seconds after the Big Bang. And there we have two very large experiments focused on understanding the electroweak phase transition and looking for the Higgs boson. And then if we go slightly delayed means 10 to the minus 5 seconds, we are looking at this phase transition from the quark-gluon plasma to particles, okay? And this is called the quark-gluon plasma phase transition. So LHC, the Large Hadron Collider, we study the first 10 to the minus 10 to 10 to the minus 5 seconds. And how can that be done? By looking at what's coming out in these collisions. And this is the field of particle physics. I mentioned to you about the collider, right? If you look on this picture here, you see on the left is France, on the right is Geneva, is Switzerland. In front are the beautiful Alps, which you see sometimes in our Bollywood movies as well. And nobody on the surface, in terms of the local residents and the cows that are grazing on the meadows, imagine that protons are whizzing around 100 kilometers underground without any passports, and they are crossing the border, and they are colliding 40 million times per second. Now, the data taking started in 2010, as I mentioned, and by now, that is in 10 years or less than 10 years, each experiment has about 1,000 peer-reviewed scientific papers. So 2 experiments, 2,000 publications. But what have we done? Are the quarks the elementary particles? So far, yes. Did we see any special particles, supersymmetric particles? maybe dark matter hints? Not yet. Do we see any extra space dimensions? Not yet. Do we see any micro black holes? Not yet. But did we see something special? Yes, we did. And we saw the discovery of a Higgs-like particle. So in 1964, there was this group of physicists which were independently working on proposing an explanation of how particles get mass. And it was Professor Higgs, after which this particle has been named, who is right here. Professor Higgs is right here. And you see there the other professors from Belgium and from England who proposed this. The theory has been called the Brout-Engler-Higgs field. And the more a particle interacts with this invisible field, the more mass it gets. So it's difficult to understand how mathematically this had been postulated, and it's even more difficult to prove that it actually exists. If the field is invisible, how do you show that it exists? And we did find the Higgs boson. And that's the Higgs boson which completes our so-called standard model of particle physics, which means the three families, the two lepton families here, and also the Higgs boson, which is the carrier of the mass, so to speak, that it gives mass to the particles. Now, looking for the Higgs has been very, very difficult. It's as if you have to find a needle in a haystack. I would rather say that you have to find one golden grain of sand on all the beach of Goa. Okay? That's the kind of difficulty in terms of data, in terms of the algorithms, in terms of triggering on what data to look at. And this Higgs, first of all, it's very heavy. So obviously to create it, we needed high energy. And not only high energy, but it's also very rare. So when it's so rare, it's not produced all the time. So it took us an equivalent of 48 years to find one Higgs boson. And that was found in the year 2012, when it was announced to the whole world. And in 2013, the Nobel Prize was then announced. Now, how is this done? This very huge collaborative experience, it's unbelievable. It's done by using accelerators, the Large Hadron Collider that I mentioned to you, detectors, they are like the microscopes, which are sitting on various points of the accelerator. And they are these gigantic instruments that are recording the stream of particles that are coming out from the collisions. Now, very good, big stream of particles. If we keep all the data that we collect, it will become a data house from the Earth to Mars. We have to clean up the data pretty much online and keep only good data. So computing is a very important element of our experiments to collect, store, distribute, and analyze the very vast amount of data that is produced by these detectors. And all that is impossible without the thousands of scientists, engineers, technicians, students, support staff to design, build, and operate these complex machines. I have been working already 25 years on this particular experiment. So imagine people had already thought of the experiment 10 years ago and had started planning and executing it. And the experiment will still continue for another 15 years. So let's look inside the machine. The machine is a proton-proton collider, and it's a discovery machine. And it runs at 13 TeV, which means 6.5 on 6.5. You look at these two pieces over here. These two faces are the beam pipes, which have very high vacuum. The LHC is truly an extraordinary machine. It is colder than the empty space in the universe because it operates with cryogenics, superconductors, superconducting magnets that operate at 1.9 degree above absolute zero. And it's very hot as well, as I mentioned already, because every time these collisions happen, the temperature over there is 1 billion times the one in the center of the sun. So these are our two experiments. On the left, you see the ATLAS experiment. On the right, you see the CMS experiment. So these are very, very big machines, or I would say detectors, or even, how can I say, let us think about a big spaceship, okay? If you look carefully, you see the sketch of a man or a woman here. So that's the scale. It's like a 6-storied building, and it's built as if this is a cylindrical onion. So think about a huge, very large, 50 meters by 25 meters of a cylinder, which is made up of layers of cylindrical onion. Okay, and then you slice the onion in every direction. Then every cell of the onion is a detector that is detecting, and that has been made specifically for detecting different kind of particles, and they are dedicated for certain kinds of decays of the Higgs boson in this particular case, but in general for studying everything that comes out from the collisions. So I hope you appreciate the complexity of the ATLAS experiment and the CMS experiment. I work on the CMS experiment, and my specialty is on the muon detectors, because muons are particles that go through all the material in front of it, and then you can detect cleanly the decay of the Higgs boson. And of course, the central detectors are the heart of the experiment. They are made out of silicon. There are pixel detectors. There are tracking detectors, which are very fast because A, they are taking data 40 million times a second, and B, there are detectors that tell us which data to keep and which data not to keep. So those are trigger detectors as well. So it is a very complex algorithms running in every part of this detection system. A few pictures to show you how it actually looks like. So this is the cavern underground, and underground you see some of my colleagues, they are working, they are fixing something, repairing things. Some more pictures just to show you elements of the detector. Now this is another element of the detector, and in this particular picture you can see it is being lowered down in the cavern. This particular object is 2,200 tons. Now you can imagine which kind of machine or which kind of a crane can actually lower this kind of a weight. So 25 years ago, it was impossible even to imagine which technologies will be used in this experiment today. But it's the foresight of our and vision of the spokespeople of our experiment who have gotten their heads together and planned in a certain direction that we work together with industry to create solutions as we go along. That's me. I'm also, as you see, sometimes working in on the field, and I have a training to drive one of these machines where I can go up on this elevated platform, although it's rather, how can I say, scary and dizzying sometimes for me, but I have now younger colleagues who do the job, and this is the installation of one of my detectors on which I have been working for last 10 years. And if anybody wants to see, they can watch this live installation of this detector. So yeah, data challenge I mentioned already, that when we planned the experiment at that point of time, the expectation was that we will be producing about 15 million gigabytes of data per year. But what we did, finally, we got something like 100 petabytes of data. So analyzing the data requires the computing power equivalent of 100,000 of today's fastest PC processors and even more. So CERN does not have that capacity, and that gave rise to distributed computing, grid computing. And that's how the Tier 0 was formed at CERN. There are Tier 1 sites in 13 different institutions, Tier 2 sites in many, many institutions, more than 150 all over the world. And it's a system of tiers where in 15 minutes, any data that is produced at CERN is then shipped off. And then now, you all younger students are going to be in charge of the second data challenge, because the CPU scaling is now coming to an end. So now we are moving towards GPU scaling, and we are preparing for exabytes because the data is going to be multiplied by 10 in the coming years. So this is an incredible challenge also in terms of software management, and artificial neural networks are used for searching exotic particles. Machine learning is used routinely to track for odd events. That's one of the collisions, how it looks like. This is a reconstruction, of course, inside the detector. And this is also another another collision where you see the Higgs being produced and then it decays into two photons. And here you see the two photons that are then caught by calorimeters. And I will not go into too much of detail. But then in summer 2012, as I mentioned earlier, there was a little blip that was found in a lot of the background, background meaning a lot of data that was taken. And this blip was eventually identified and certified with large confidence to be the Higgs boson. And this was announced on July 4th, 2012. And it was an official seminar at CERN where I woke up at 5 o'clock to go and watch this seminar. Still for a physics conference that was happening in Melbourne, in Australia, and of course it was followed live all over the world. Eventually it was covered by media all over the world as well, and eventually in October 2013, Peter Higgs and Francois Englert got the Nobel Prize for postulating the Higgs mechanism for giving mass to particles, and to CERN for the CMS and ATLAS experiments to actually observe the Higgs boson. So this is a very interesting long story of participation, collaboration, and the immense value that has been given in this particular case to the collaboration of large number of scientists, in this case, the largest scientific collaboration on the planet. The future, of course, lies in studying the Higgs. It's a newborn baby. So yeah, what next? So we want to understand that why the Higgs has a mass, what it has, and what explains the mass pattern. We do not understand that as well. What is the connection with dark matter and where is the antimatter? So these searches are going on. And the next challenge, of course, is to look for supersymmetric particles, dark matter, dark energy, and so on. So now, moving towards applications now, why did I go through all the story of what we are doing at CERN is to explain to you the complexity of every aspect of what we do. So we work on technologies. There are a big group of theoretical physicists who are working on the physics. And of course, the moment we create a tool, we are able to look for new physics, or we are able to look for solutions to ongoing problems. So the interface between fundamental science and the technology itself is very, very fundamental. So, and then of course, you all have heard about www, not only heard, you use it in every single day, and there is no day that goes without typing www on the internet window, right? And I hope that many of you know that it was invented at CERN by a 22-year-old student who wanted to come and share data, this kind of data that we spoke about, between the physicists all over the world. And when he came and proposed this with a sketch to his supervisor, that if we use HTTP, we might be able to share data between computers which are remote from each other. His supervisor said, he wrote on that paper, which now is in our museum and exhibition at CERN, his supervisor wrote, vague but exciting. And you see what has happened 30 years hence, its history. So, accelerating beams, detecting particles, and of course, large-scale computing grid. These are the three pillars on which our experiments are based. And of course, there are many, many, many applications. I've just picked up a few and then we go to them. So one of the applications that I want to speak about is medical applications. Because when you combine physics, internet, computing, biology, and medicine, we will be able to fight cancer. You know, by using X-rays, we already have a lot of treatment worldwide for, if you look on this picture, which I'm showing here, you have the irradiation of the tumor and a lot of irradiation of the healthy tissue around it as well. But if you were to use accelerating particle beams, with protons or with other ions, you can contain and you can pinpoint all the desired energy loss from the beam to the tumor itself. And that has made a very big difference in the life of patients, in the treatment of patients worldwide. And there are many, many facilities. So this has been an immediate spin-off that has come out. And of course, just like we detect particles, we can then do imaging. And all the imaging that you see on PET scans and all the other different kinds of scanning machines that you see in the hospitals, which are now routine, are coming by using the detection schemes that we have produced to measure particles around the collision points. And that's exactly what we do when we are doing the imaging in the hospitals. Now here you see a little USB stick, right? And this is on the space station. So what is this USB stick doing here? Let's see further. And do you see the sign of CERN? I just noticed, by the way, you see the sign of CERN here. This is incredible. So one kind of detectors that we use very close to the collision point are called hybrid silicon pixel detectors. And these detectors essentially use a silicon layer whereby any radiation that will go through will liberate electrons, and these electrons will be picked up by pixels or by readout strips or whatever you wish to, as you see, and you will be able to read out every single pixel. And this is a highly miniaturized version of the large detector that you have seen. You are actually able to have radiation monitoring by using a very tiny chip, which are very dense, and we have used in our experiments. As you see here, this is a bump bond, so to speak, where a very, very tiny bond can be made between every single pixel that you can read out from a silicon detector. In addition, the electronics has now gone so far ahead that we are able to have a very low noise when we make images with this detector, which is actually for the high energy physics needed use them. So this is the way we use the detectors in high energy physics. You see the pixel detector here. The detector itself, it was its production, making modules, putting in the large detector at large experiment, CMS, underground, and then bang, here you see all the particles that are coming out from the collisions. And if you miniaturize what we have just seen, you are able to have a readout that you can just plug in with a USB stick. And over here, you will be able to measure the radiation, whatever you wish to do. Since the background is so low, you are able to have a very good contrast as well when you are making images using this kind of Medipix devices that I just showed you. Again, this is a color X-ray of a lighter. See, it's quite interesting, isn't it? That you are able to completely see through with very high precision, and that has ample applications in many fields, including the, now here, look at this, how beautiful this is. All right, look at this one as well, spectroscopic information. You can separate the density of material that you see when you are doing imaging. That's a small scale. This is a wrist of one of our colleagues. And I'll just flash through some images. You can just see the beauty of these detectors, that you are able to see through a 3D solid body by using these very tiny detectors. Now, here again, we go to another application. This is for research in schools. And these detectors that we have made, the USB detectors, can actually be used for teaching in schools. Now, here is another test flight I want to show you, which has, again, these chips inside these very large battery-operated independent radiation detector that has been launched. And you see the Timepix chip is actually sitting on board, which is a very small small detector here. Then you all know that every time we travel by air, we are hit by radiation, and one trajectory is equivalent to an X-ray that we get when we do go to the hospital. So this is something that needs to be monitored, and to monitor that we need instruments, and they are used in space, they are used in aircrafts, And every time the dose that is needed to be calculated for pilots and for astronauts, these detectors are used. So here is Tim Berners-Lee, who has invented the World Wide Web at CERN. X-rays I mentioned, and of course digital imaging as well is quite in vogue now. And apart from that, a lot of simulations are needed before we actually launch into these big experiments. Because you will ask me that we are spending billions of dollars doing these experiments. Why should we have this money to do these experiments? So we need to convince ourselves that we are actually going to have extremely good simulations that tell us that what we have predicted will be, in fact, useful in every single way, not only for the fundamental understanding of matter and fundamental understanding and furthering knowledge as such, but also with a big societal impact. In addition, we can use grid computing in these very many ways, as you see here in bioinformatics, in education and training, in meteorological weather forecasting. We can save human lives, and this is actually happening. It's not only because simulations of these kinds need, they are very memory hungry, as you can imagine, and the grid computing is now very, very much used and is also been upgraded very recently for all these applications. Here we have some collaboration and exercise which is happening between CERN and European Space Agency over here. And as I already mentioned to you, that the vacuum that we have here is of very big interest to the space industry. The vacuums and the temperatures, the materials that we use, they are very, very, we work together to create these kind of materials that are radiation resistant and that can operate in very different temperatures. In addition, radiation management, I already mentioned to you, the big data I already mentioned as well. And not only does CERN do all the kind of experiments that I mentioned before, but we also have some examples with collaboration and experiments in space. And these are sitting at the space station, at the International Space Station. These buildings are at CERN, where the detectors have been built, and eventually they have been installed at the space station. Yes, we had a visit of Richard Branson as well, who brings Virgin Atlantic to CERN, and he is looking into the kind of technologies that we can work together towards taking this team and taking applications from all the various technologies that we could possibly use in Virgin Galactic. A team at CERN is also working with the European Space Radiation Superconducting Shield Project to develop a superconducting magnet that could protect astronauts from cosmic radiations during deep space missions. The idea is to create an active magnetic field to shield the spacecraft from high-energy particles. You may have heard of accidents that sometimes happen to pilots when a very high-energy particle from cosmic rays goes through his iris or goes through the eye. So definitely we can do some improvement there, and superconducting coils and superconducting magnets are a big specialty of CERN and the accelerator department. So these are just some more examples, and you can browse at leisure on the experiments where we are developing radiation tolerant systems for space. So my last point I want to make about the work here is about collaboration. As you see, this is just part of the collaborations that you see here, because we, in one experiment, we are about more than 5,000 people that work together. And collaboration itself has very, very clear, how can I say, very unique, how should I say, put it there, unique manner of working, I would, right? Because when we are working together, when we are working in small teams, of course, we are very productive and we certainly can do the best we are able to. But when we come together as a collaboration to tackle large problems in the world, and we come together as a very large collaboration, the whole scientific community works together if you have a problem, you just go to the next person and you ask for a solution, and you're able to find the solution. So the pace at which you learn and the pace at which you are able to work and also produce results, and you fail every day, but then you find solutions and you learn every day as well. So that's very important, and I think that has been the biggest learning that personally I have had while working on these large experiments. So, of course, in these large experiments, there are clear definitions, there are agreements on roles, there are structures, but there is open communication as well. There's a lot of recognition on for the youngest person and the most senior person as well. And cooperatively, we have been addressing problems. And of course, teamwork is great. So now that we know, we are looking for the ingredients of the cosmic soup. We are continuing to upgrade our experiments. We are continuing to work together. And there is a lot of data that's coming, which will come for the next 20 years. So in retrospect, CMS or the LHC has been a program that has been here already for 30 years, and it's going to run for another 15, 20 years, which means that this is a good part of anybody's career, and it's not simulation phase and concepts are being driven. And the next one, at least at CERN, is called the Future Circular Collider, and that has a circumference of 100 kilometers. Compare of the 27 kilometers at LHC to the 100 kilometers of FCC. And today we do not know what are the technologies that will come in 20 years. So the spirit that we have to take is to take the spirit of adventure and take the spirit of the challenge, rising up to the challenge, and then move on. And how can we move, even though we are so confused, so unclear, and kind of disoriented in terms of where to start, how to begin, how to take part? Which, I mean, as an Indian, I come from India. I come from Jhansi, a small place in India. But eventually, there are so many opportunities of participating. The data is free, is accessible, it's open access. Everybody who is willing can prepare a project and look into the data which is available. So tools today are available, and there is no stopping and there is no excuse today for not participating. As you see here, these are some students who have been at CERN, teachers who have been at CERN, and not everybody can come to CERN. So we are doing a lot of outreach work in India as well. We do not know what and how we are going to do this post-COVID era. But as you see, webinars are now very more than popular, and I'm doing literally one every other day. So I think that information is even traveling faster now than before. So yes, I think that there is a lot of scope to transform what we are doing, particularly in India. And as a single person, as a team, as a community, we are working very much together, and we are trying to inspire the scientists of tomorrow, just like you all who are studying now, and you have a big future in front of you. So my last thoughts are on sharing with you that particle physics, I hope I have convinced you, is a journey which is a long journey, and it's very multidisciplinary. And applications that start from even conceiving the technologies for the physics questions lead you to answers to the questions. Sometimes yes, sometimes not. It takes time. It's a very long process. But through the cycle of making this experiment, thinking about the whole, thinking about the whole cycle and working very hard through the cycle, one is able to go through the execution period, through the experiment, data taking, monitoring, making a physics discovery sometimes, exploiting the data, learning about big data analytics, and of course, all that prepares you to do anything. And that's what is my point really. So you have learned how to tackle data by all kinds of machine learning, artificial intelligence, analytics, and so on, all the buzzwords today. You have learned them once you have gone through this cycle. 70%, 80% of the PhD students from high energy physics, they disappear from the field. they are they are hoovered by the industry for financial management, for risk management. They know how to do all the trends, and I don't really know much about finance, but they know how to do all the risk management, for example, and so on. You've seen the mechanical engineering challenges, the material challenges, the space science kind of challenges that we have had to face, because we are looking for solutions to conditions that exist out there in space as well. And I showed you many other examples of medical imaging, industrial applications, safety, radiation monitoring, meteorology, which I didn't touch, and of course, outreach and education is natural. And in addition, project management. A project of this scale is incredible. And once you enter as a student, you are working in your own silo, in a quiet corner. But then, gently, as you grow, without knowing, you suddenly start comprehending the scale of things and the scale of the project. And project management has been an immense learning in this whole exercise as well. So, yes, at CERN, we have a mission where we are pushing back the frontiers of knowledge. We are developing new technologies for accelerators and detectors and information technology. We are training the scientists and engineers of tomorrow, and we are also uniting the people from different countries and cultures. So here I would like to stop. The woods are lovely, dark and deep, but I have promises to keep and miles to go before I sleep, and miles to go before I sleep. Thank you for your attention.
Thank you, ma'am. Now we move over to the Q&A section. Sorry, ma'am, your mic has been muted. Please
Oh,
check that.
let me. Can
Yeah, it's
somebody?
fine now.
It's okay? Okay.
Yes, ma'am, you can continue.
So why is it also called the God particle? So there are two answers to this question. One is a simple answer that where did mass come from? So God created mass. So perhaps this is the particle where God gave mass to particles, to other particles. However, the truth is that Leon Lederman, he was the director of Fermilab. It is a sister organization in the United States. They have he was writing a book, and in that book, he wanted to title the book simply because they didn't find the Higgs boson in the United States. He wanted to title the book "The Goddamn Particle," and his editor thought it was not really a good title, so he edited it to "The God Particle," and that's probably the origin of from where this God particle came. Right. So other questions. Let me start from the top. How do you contain such a high amount of concentrated energy generated from collision? So the energy is actually dissipated immediately within the meters of the experiment. It all becomes very hot, as you can imagine. There is a lot of cooling that is imparted to all the electronic components, just like your computer gets very hot, right? When I'm working with my laptop, it becomes very hot sometimes. Similarly, every electronic component, excuse me, that becomes very hot, and there is a lot of water cooling, air cooling, and all different kinds of. And in the future, there's going to be carbon dioxide cooling as well. Because you might know that there is freon that is used in cooling coolants, and that is not going. It's not a green substance, and it's going to be phased out. So now we have to move to carbon dioxide cooling. So there is a big engineering group which looks after how we cool our detectors. And the concentrated energy from the collision is converted into mass for a very brief moment of time, and then again it's dissipated in terms of energy within meters of the experiment. I hope that answers your question. What is the future of dark matter to be taken as a research field by us students? So the future of dark matter, at the moment, first of all, we have to understand what happens post COVID-19. If it is, I hope that and pray that we are all out of this nightmare very soon and we are able to do our experiments, because right now we are all stalled and all experiments are at a halt. We are working from home, but if the experiments go on, and you know that in 2020, 2022, when we will start again the accelerator, the energy will be increased, the luminosity will be increased, and then again, looking at dark matter in the data sets is one of a very big job that is open. And I certainly encourage all students who are interested in the field to study about this and to look at opportunities, for example, for doctoral opportunities or postdoctoral opportunities or engineering opportunities. I wouldn't like to limit this field to just being called a physicist sitting with equations or analysis codes. It's a whole plethora of things that you can do. Okay. What experiments going on to prove parallel universe? Look, I am not qualified to answer your question. If we find dark matter, this is going to be amazing. If we find something on entanglement, it will be super amazing. This comes to the question of next one, Ananya Munshi. The LHC is used to prove superstring theory, later symmetrical. Why doesn't the math form already prove the idea for graviton? Well, the graviton is very, very, very heavy, or supposed to be very, very heavy. So one has to actually corroborate the idea that we can produce it, or we are able to look for it. So if we are able to find a dark matter candidate, that can lead us towards telling us that the standard model is the correct model, and the graviton is another missing boson from the standard model. So I'm not an expert, but yes, that's the direction probably we is there a possibility to find Higgs boson near a black hole? I think possibility always exists, and Higgs bosons are not stable, as you know. We are 14 billion years away from the Big Bang. So if there is a stroke of luck, which is 10 to the 38 seconds, which is I don't know how many years or light years, there could be such a case. What is nagging problem in terms of stiffness-based phenotyping? I'm sorry, I cannot answer this question. Okay, these are the questions. Are there any more questions? But these are the ones that I see in my chat window. Any other question? Hello? Can you still hear me?
I request the moderators to kindly resend the questions.
What will be prediction for large collider experiments? Well, there is all the phase that I explained a bit earlier on the electroweak sector, and also the dark matter sector, the dark energy sector. We have to see these kind of which sector to take. And for the large colliders, whether we will go for electron-electron collider, or whether we will go for electron-hadron collider, or we will go for hadron-hadron collider. These are the questions that are being talked about. Okay. Yes, Rohit Sansia is saying about several applications, including wearable sensors for real-time UV radiation monitoring, spaceborne images for UV. Okay, good. Noted. So Dan Brown, somebody is asking. Well, I think that there is 2% fact and the rest is fiction in the book, simply because, antimatter exists. That is the truth. We have found antimatter, we have trapped antimatter, and antimatter is used in hospitals. So that much is true, and the rest is fiction, of course. Then fundamental difference between antimatter and matter. So fundamental difference between matter and antimatter, first of all, it's the charges. If matter has charge, an electron has a charge negative, a positron has a charge plus. So any attribute of a matter particle is negative for the antimatter particle. So one has to understand how what is different. Is the way antimatter behaves under gravity different? Is the way antimatter interacts with each other in presence of other forces different as compared to matter or not? So these are the questions that are open, and we have to study this. There is another experiment which I didn't mention clearly in my talk, that is the LHCb experiment, which is looking at the decay of the B quarks and the formation of different kinds of quarklets, if I can say, like pentaquark, like and tetraquark. So these kind of particles can give us hints towards different kind of first of all, matter and antimatter asymmetry, because the bottom and the anti-bottom quark, how they will decay, will tell you on the difference between the matter and antimatter, and and also give clues to the dark matter as well. Other questions? How fatal it can be if any part of collider fails to work properly. So clearly, I mean, think about your home. If one pipe doesn't work, you have valves on the other side to switch them off. In addition, there are signals and sensors in every place at the experiment. As far as we can, we have to have monitoring going on, safety monitoring. We have to have immediate intimation if there is any failure, and immediate action is taken. Most of this is done automatically. Most of the monitoring is done automatically in a fail-safe mode, and everything comes to your phone. You know, if there is some message, that messaging will come immediately if there is any failure anywhere. So yes, it's just like, how can I say, you may have heard in 2010, in 2008, sorry, when the LHC first started, there was a little problem between an interconnect of one big superconducting magnet and the next one because of the slightly higher resistance. And following that, we had to instrument monitors all around to measure this current in the resistance before we could actually restart the LHC. And that took 2 years. That is why data taking started in 2010. So monitoring, safety and monitoring is extremely important, and we have to secure every possible predicted failure beforehand, do a risk analysis, and be very prepared. What is the other question? Is hadron therapy used for removing viral particles? I'm afraid not, sir, because hadron therapy really deposits a lot of energy. It can be used for looking at the conditions of the lungs, not hadron therapy, but imaging can be used for looking at the conditions of the lung by using high contrast medical imaging. Okay, I have exhausted the questions. Can students from BVM have remote internship at CERN? Last question. So this year, unfortunately, all internships at CERN have been cancelled. They are looking into how to do remote internships, and there will be some information that will come out. And of course, today you will have all the information on the net. You have all the career options also on the net. Just browse careers.cern.ch and you will find a lot of opportunities. If you still have questions, you contact me and I will try to solve or at least give you some guidance. And personally, also, I have a lot of interns who work with me, as you have seen in some of the pictures. And there are many, many projects that can be done depending on the interest of the students that can be done remotely. Thank you. Yes, for unsolved problems, yes. Material science is very important. It comes to mind. Polymer science is very important, and so on. Yeah. All right.
Yeah. Thank you, ma'am. A very good evening to one and all present over here. I, Parsha, Treasurer, IEEE BVM Student Trans. First of all, Dr. Archana Sharma, ma'am, the whole team IEEE BVM SB is extremely delighted and honored to get the opportunity to attend this session from you. Your amazing and informative session surely reverberates in our mind and make us feel different about our existence in this world as well as the universe. Ma'am, we heartily appreciate all the time you have taken from your busy schedule to spread knowledge and help us in achieving our vision of driving people from the darkness of this pandemic to light. We are amazed to know about CERN and are proud to know about your contribution to mankind for a better future. We are proud to have our enthusiastic Indians like you being a major part of world development. We thank you for this amazing session and we look forward to have you with us in the near future since we can never get enough of someone so kind and knowledgeable. Thank you for sharing your knowledge with us. Now, I would like to call Darshan Dalwadi sir, Branch Councillor of IEEE BVM Student Branch, to say a few words.
So first of all, I want to thank Madam Dr. Archana Sharma for such an informative session. It was excellent session, Madam. Thank you very much. It surely helped everyone learn something new. I thank our Principal Sir, Dr. Indrajit Patel Sir, for supporting us, and our today host Himanshu Thakur and Patsha, along with the moderators of the day, Atharva Bhave and Gaurav Bharve, for handling everything during the session. To make it effective, I would like to thank Team IEEE BVM for organizing this event and all the dear participants without whom we would not be able to spread the knowledge. I hope everyone enjoyed the session and we will meet soon again in our next session tomorrow. Tomorrow is our last session at 4 p.m. by Mr. Farid Khan, Chair South Asia IEEE, the session on future smart cities. So stay safe and stay home, everyone. Thank you very much. Thank you.
Thank you very much, everyone. Thank you. Stay safe. Bye-bye.
Thank you, sir. And before ending this session, I would like to remind everyone about our upcoming blog writing competition, blogathon. The registration are open now, so kindly go ahead and register as soon as possible. Further details are given in the chat box. And yes, we have another surprise event for you on May 1st. We are coming up with a short session on basic of blog writing by scientific blogger Vallabh Shah here on YouTube. So do join us on that and get started with your own blogs. I once again thank you, Archana ma'am, and thank you everyone for joining in.